Hi, this is Dave Johnson with another edition of Math Off Topics. Today I'm going to solve a differential equation which will calculate the reentry velocity of an object into the Earth's atmosphere, starting from free fall at the lunar orbit. Why might this be relevant? Well, a little more than a year ago, NASA sent up Artemis I. Artemis is the lunar landing program that NASA is undertaking. Artemis I went around the moon and came back to Earth. And at the time, they put out a video of a depiction of the orbital changes and so on in an Earth-centered frame of reference. So I'm going to show you that video today because it's kind of cool, and then write down and solve the corresponding differential equation and see if we can get the same answer that NASA gets. Okay, so let's get into it. So this is the video. The green is the moon, of course, and the pink is the Artemis spacecraft. And you can see that the moon grabbed Artemis, and Artemis is now chasing the moon around, and Artemis is going to catch up to the moon. And right here, Artemis uses the moon's gravitational field to stop it dead in its tracks, and from there it's going to free fall back to the Earth. Let's run that once more just to make sure we see the whole thing. So launch Artemis, moon grabs it, sends it ahead of the moon. Moon catches up. Artemis then catches back up to the moon, is stopped by moon's gravitational field, and then falls back in free fall toward the Earth. Now, of course, I don't work for NASA. I'm not an expert in orbital mechanics, but this was pretty fascinating to me. And so I thought, well, maybe we can write down a differential equation that would correctly calculate the re-entry velocity. And one more time, I know this. I don't want this to get tedious, but I don't know if you can see in the lower left that I believe is the velocity of Artemis. And when the moon grabs it, you'll see that it almost goes to zero right there. And then it's falling back to the Earth, and it's going to speed up, and it gets to, you can't see it right at the end there, but it's about 10 kilometers per second, which works out to be somewhere around 20 some thousand miles per hour. So let's do the let's solve the differential equation. And by the way, the actual Artemis spacecraft will not be re-entering the Earth's atmosphere. It'll be the Orion, which is basically the capsule which will hold the astronauts on their return trip to the Earth. And so, what would be the appropriate differential equation? Well, uh, Newton's law of gravity, G times m. I'm going to use m sub e for the mass of the Earth, and then little m for the mass of the Orion spacecraft divided by r squared. And that's going to equal the negative of the force. So the force is directed towards the Earth. That's the meaning of the minus sign. We know that force is equal to mass times acceleration. So I'm going to say this is equal to negative ma. Now, if you look at this differential, is it even a differential equation at this point? Well, not exactly, not yet, because there's no derivative in this expression. Now, you might say, well, wait a minute, there's a derivative in the acceleration. Okay, let's write that out. So we get negative m times d squared r dt squared, so d squared r dt squared. And I can write that as negative m times d, that's supposed to be squared there, d by dt of dr dt. Okay. Now, before I go on, let's simplify a little bit here. So I'm going to cancel the little m's. So whatever result we have is not going to depend on the mass of the Orion capsule. And what I want to do now is I want to replace the drdt with something. Now, why do we how are we going to modify this differential equation to make it something useful? What we want is the velocity. In this equation, we don't have the velocity yet. So, but drdt is the velocity. Okay, so I'm going to write that as v. But we also don't care about the time. I mean, of course, the astronauts care about the time. NASA cares about the time, but we don't. We just want to know what is going to be the final velocity when it reaches a certain distance from the center of the Earth. And so we're going to end up doing a little bit more manipulation here, but so that we get negative d by dt of v, drdt is v. So I'm going to write this as negative dv dt. But again, we want to get rid of the t dependence. So let me give myself a little bit more room here. If we use the chain rule, so negative dv dt is the same as negative we want the derivative with respect to r. And so we can do that. We can say dv dt is the same as dv dr times dr dt. So I'm just applying the chain rule to dv dt. And now I'm going to again replace this with v. And so we get gm sub e divide by, I canceled the little m, divide by r squared is equal to negative dv dr times v. Okay. So let me rewrite this. I'm going to multiply both sides by dr, put the negative sign on the other side, and write it this way. So v dv is equal to negative gm sub e times dr divided by r squared. And this is going to be the differential equation that we're going to solve. And we can do this, it's separable. I've separated the variables. I've got the v's on one side, the r's on the other side. And so let's go ahead and integrate both sides. So the integral of v dv is equal to the integral of negative gm sub e dr divided by r squared. I'm not using limits on the integral because I'm going to use a arbitrary constant and figure out what that arbitrary constant is. We don't have to do it that way, but that's one way to do it. So we get on the left side v squared divided by 2, so that's the integral of v. And on the right side, let me bring out the negative gm sub e, so negative gm sub e, and then the integral, so that's r to the negative 2, and the integral of that is going to be r to the negative 1 divided by negative 1. So if I divide by negative 1 here and then put an r downstairs, that's going to be the integral. And we want our arbitrary constant. So let me just say plus c. Okay. Now these negative signs cancel, so we get g m sub e divided by r plus c. Okay. So at this point, maybe we want to figure out what c is. Well, let's assume that at r, so I'll say this, at r moon, and I have the number for that, it's about 3.85 times 10 to the 8th meters And so I'm just going to use r sub m for that. That's the distance, the average distance of the moon from the Earth. And so if we plug that in to r, the v at that point should be 0. So v would be equal to 0. I'm assuming, that once the moon has released the Orion spacecraft, and now the Orion is in free fall, it starts at 0 velocity. So on the left side, we'll get 0. And if I add, well, let me go ahead and write it this way. So 0 is equal to negative gm sub e. Actually, I'm canceling the negatives. So over r sub m. And then plus c. And when we solve for c, we get the c is equal to the negative of g m sub e divided by r sub m. Okay, so we're almost there. Let me solve now for v squared. So it's going to multiply by 2. So we get v squared is equal to 2g m sub e divided by r plus the negative 2g m sub e divided by r sub m. And so we get 2g m sub e times the quantity 1 over r minus 1 over r sub m. Now, what is r? R is the distance from the Earth, from the center of the Earth, at which we want to know what the velocity is. So one last thing we'll do, we'll take the square root. We get v is equal to, it's going to be a positive square root. So square root of 2g m sub e times 1 over r minus 1 over r sub m. And if you plug in the numbers, and let's use r here to be the radius of the Earth plus about 30 kilometers for the where it enters the atmosphere. So if you take the radius of the Earth and you add 30 kilometers, you get about 6.408 times 10 to the 6th meters. And if you plug those numbers in, and using the expression for g, which I probably should tell you, g is equal to 6.67 times 10 to the negative 11 meters cubed divided by kilogram second squared. And if you plug all those numbers in, you get 11,059 meters per second, which ends up being about 24,737 miles per hour. And that's not exactly what the video showed, but it's pretty close. And so I hope this has been helpful and interesting. And if so, please like and subscribe. And I'll see you in the next video.